Hey y'all, it's your personal math teacher, Mr. Boyd, and I'm back at it again. And today we're going to learn about a new type of significance test, specifically a significance test for a mean to predict mu. It's going to be similar to what we did in the previous video, and anytime we have a question involving a significance test for a mean, we're still going to write out a state, plan, do, and interpret, and it works the exact same way that we saw for proportions. So here's what I want you to get out of this video today. First of all, I want you to know which kind of test we use when we're dealing with a mean. I want you to have the calculator skills to do that successfully, whether you're given data or whether you're given statistics. And then we're also going to practice, or we're going to learn what the power of a test is. Okay, so let's get right into it. So first things first, we're doing a test about a mean. And let's remember what we learned about in confidence intervals, specifically with the critical value. Sometimes it was z star for the critical value, and sometimes it was t. When it was a mean, it was t. And so what that means is we really only want to look at the things that have a t in them. And it makes it pretty easy because we have a t-test right here, and we have a two-sample t-test right here. Now, down at the bottom, there is like a two-sample f-test or a linear regression t-test. We're not going to use those right now. We'll learn later what those are. Okay, so what it comes down to is you have to look at and see, do I have one sample or do I have two? If it's one sample, it's a regular t-test. If you took two samples and you're comparing them to one another, then it's a two-sample t-test. Okay, so let's talk about conditions that need to be satisfied. Unsurprisingly, we need to satisfy the randomness condition. So we need a random sample, or if it's an experiment, random assignment. Random, got to work on my spelling this morning. We do have to satisfy the 10% condition, and then we have to establish normality of the sampling distribution. So normality. And remember, there's a few ways that that could happen. They could tell us. It could be satisfied with the central limit theorem. That's my personal favorite. Or it could be that we see no skewness or outliers in our sample. So no skew or outliers in sample. So those are the things we're going to look for. Anytime you have a free response question or a test question, assume that you're going to have to, before doing the t-test, you're going to have to actually run through these conditions. Okay. In the previous video, the one about proportions, we saw this. Okay. We saw that basically we're going to end up with our standardized test statistic, and for a proportion it was z. For a mean, it's not going to be z, it's going to be t. And it's going to work the same way as a z-score. So it's going to be the statistic minus the parameter divided by the standard deviation. So right here, this was last video. What is it going to look like for a mean? Well, it's going to swap all these things out for things that relate to means. It's going to look like this. So we have our statistic minus the mean. And notice that's basically saying right there, that's the null value. Null value. And then this is the standard deviation of the sampling distribution. Okay, in the same way that in the example above with proportions, that thing in the denominator was also the standard deviation of the sampling distribution. That one's just the standard deviation for the proportion though. So enough talk, let's get into an example. The distribution of IQ scores for the adult population is approximately normal with mean 100. Mr. Boyden's class hypothesizes that teachers who teach AP classes have higher than average IQ. So they select a random sample of 10 AP teachers and record their IQ scores. The results are as follows, and there's the scores right there. Question: do the data provide convincing evidence at the alpha equals 0.05 level that AP teachers have a higher mean IQ score than the general adult population? And then they're also going to ask, given our conclusion to part A, what type of error might we have made, type 1 or type 2, and what are the possible consequences of that in this context? So let's think first about our conditions. We need randomness. So do we have that? Absolutely. We have a random sample. We need to satisfy the 10% condition. Do we do that? Yeah, this is a sample size of 10. 10 is definitely less than 10% of all the teachers that teach AP. And what about skewness? I don't know. Let's type these in our calculator and let's see, because it doesn't satisfy the large counts condition, although actually you may have noticed they said that we are sampling from an approximately normal population. So that satisfies the normality condition. So we were actually told right there. So let's take a minute and get these data in our calculator. And so give yourself a lists and spreadsheets screen. And let's fill in the scores. Now that we have our scores typed in, we are almost ready to run our significance test. Let's return to the question for a moment. One thing we'll need to do before we can even dream about writing out that information is we need to figure out what our hypotheses are. So our null and our alternative. So our null is the conventional wisdom that the mean is 100. So the mean is 100. The alternative hypothesis that the mean is, we hypothesize that they are going to be higher than average, so greater than 100, where mu is the mean IQ of AP teachers. And X bar is going to be our sample mean. And do we know that? We don't yet. So I'm not even going to fill that in yet. I actually want to put a number right there. Okay, so that's the state part of the question. Let's do the plan. The plan is a t-test. And our conditions are randomness. Yes, we were told random sample. So check the 10% condition. And I'm going to say 10 is less than 10% of all AP teachers. And then for the normality condition, oh, don't forget your check mark over here. And then for the normality condition, we're going to say they gave us the phrase approximately normal. And so we are good to run this test. Let's return to the calculator, and because now we're on to the do part. And we need to go get some of those values. So here we go. Off to the calculator. You're going to need to add a new page. So Control Doc to add that new page. And this one needs to be a calculator page. All of our tests and confidence intervals will be built on a calculator page. So they all work the same way. Let's go to the menu. Everything good happens there. Statistics. We're going to be doing stats tests. And we only had one sample here, so this is a t-test. Now, what's our input method going to be? We just filled in data. So the other option is statistics. We actually don't have the statistics. We have the data, so stick with that. And then what is our null value? Our null value, we wrote that in our null hypothesis. That was 100. We need to let them know what list we want. We want the IQ list of those data that we had. Don't worry about the frequency list. That basically never comes up in this class. So don't change it either though. And then we said that we thought the mean was going to be higher than the null value. So we need to pick the alternative hypothesis that matches. And let's see what we get. All right. Interesting stuff. So remember before I waited to fill in the statistic up at the very top in the state part of our answer? So one reason I did that is because I knew that they were going to spoon feed it to us right here. So let's pull that value. Let's also take our p-value and our test statistic. Let's return those back over to our notebook here. And so up at the top, I can fill in that the mean for the AP teachers was 108.3. And the question will be, is that a big enough difference to say that, in fact, yes, we believe that AP teachers on average have a higher IQ than the average population? All right, so what do we have? We know that our value of t is 2.763, and our p-value was 0.011, And please draw a picture. Remember, this is a t-distribution, but t-distributions, when you sketch them, they look like normal distributions. We just understand from the previous unit they're a little bit more spread out, so that's totally fine. So 0's in the middle, 2.763 is somewhere over here. And then this said greater than, so we're shading to the right, and that's a little tiny tail area of 0.011. That's the p-value. All right, now we get to do the interpret. I mean, sometimes you're going to see this is called conclude. I like interpret, but both are good. By the way, on the AP exam, they're not actually scoring what word you write there. This is just a basic guideline to make sure that you give all the information that's needed for a rubric. So now we get to interpret this. So to do that, we're going to look at our p-value. Our p-value is right here. Is that sufficiently small? Well, let's see. We need to know what the significance level is. Let's go back up. We were told the significance level is 0.05. So, yep, that's smaller than 0.05. So what we'll say is, since our p-value, which was 0.011, is less than the given alpha, which is 0.05, we reject the null hypothesis. And specifically in context, that means there is convincing evidence that the mean IQ of AP teachers is higher than the adult population. I should say than the average of the adult population. All right, y'all, and that's complete. So notice the mechanics of this are basically exactly the same as a proportion. What was different? Well, it's a mean technically, and we use a different test, but it works the exact same way. Now, part B asks us, what type of error, 1 or 2, might we have committed here? And what might that mean in this context? What might be the consequences of that? So in this example, we rejected the null. Okay, we would call that a positive result. So it's possible that we had a false positive. And we remember that a false positive is a type 1 error. So we may have committed a type 1 error here. We don't know, but it's a possibility. Now, what are the consequences of that? That would mean that we think that the mean IQ of AP teachers is higher than the adult population, when in fact it's not. So what would that do? It would certainly make us look arrogant as AP teachers if we thought that, or as a class if you thought, well, my AP teachers are so smart. And if they're actually not, on average, having a higher IQ than the population, then I don't think there's anything horrible that comes out of that other than maybe some social consequences related to arrogance or thinking that you're better than somebody else or something like that, which is something we'd obviously want to be careful about anyway. Right? Now we need to talk about the power of a test. The power of a test has a tendency to be a little bit confusing at first. Okay, and it is a vocab word. It's actually a number. The power of a test is a number that you'll be given sometimes. Usually in an AP exam, they'll give you the number for the power and you'll have to interpret it, or you'll have to, it's a classic multiple choice question that you'll have to explain which of these things would increase the power of the test or which of these things would decrease. Okay, so the definition, specifically the power is the same thing as the probability of avoiding a type 2 error. Okay, now that's the same thing as a test being sensitive. A test is sensitive if it's really unlikely to have a false negative. So if your power is high, and specifically this is high power, that would mean that false negatives are unlikely. So that would tell you that if you got a negative result, now negative result, by the way, would be failing to reject the null. That would be a negative, means you didn't find the evidence. So if you get a negative result, if you end up failing to reject and the power is high, you can be relatively certain that that's the correct conclusion to come to. Okay, and that's why this would be useful. Okay, we can also put it in an equation form. It is 1 minus the probability of a type 2 error. That's what we mean by the probability of avoiding a type 2 error, the probability of not having a type 2 error. It's that complementary probability. Okay, and another way yet of understanding it is that it's the probability that we find convincing evidence for the alternative when the alternative is true. So it's like the probability that we correctly rejected the null. Okay, so that might seem like a lot of stuff. I think this table can summarize a lot of the things that we've learned in the last 2 lessons. Okay, and here it is. The only issue that I have with this table is right here. It says accept the null. That shouldn't say accept, it should say fail to reject. So I don't know who made that, but that's okay. The rest of what they did here is really good. So reject. And so let's look at what they have here. This is all the different things, all the possible results that can occur when you run a significance test. The first thing that could happen is if in actuality the null is true and you fail to reject, then you have a correct result. Okay? The probability of that happening is 1 minus alpha. That's the same thing as the confidence level, the probability of that happening, okay, if it's true. And then alpha would be the error rate, the type 1 error rate. That's what we saw last time. A type 1 error rate is when the null is true, but you reject the null anyway. So that's a false positive, meaning you found evidence to reject. And we learned in the previous video that the probability of doing that is the significance level. Okay, so that's what alpha is. Okay, now what if in fact the null hypothesis is false, if it's not true? Okay, but this box right here is saying if the null was false but we didn't find evidence, that would be the equivalent of a false negative. And the probability of a type 2 error is beta. Okay? Versus over here, the power is 1 minus that probability, which is exactly what we saw above. And so this is, again, avoiding a type 2 error. Beta is your probability of a false negative. So 1 minus beta is your probability of avoiding a false negative. And alpha is your false positive percentage, or your false positive rate, where 1 minus alpha is your probability of avoiding a type 1 error. So I want to encourage you to pause the video and write this down. This is something that as we go forward, it can be kind of helpful for the first couple days that you're practicing and as you review and all that. So I encourage you to pause this before you continue the video. The CDC claims that 11% of children have ADHD. A company claims it has a new vitamin tablet that lowers a child's risk for developing ADHD. Researchers administered the tablet to 200 children, and the subjects are going to be tracked through their childhood with researchers recording the proportion of subjects who develop ADHD, with a null hypothesis of the proportion being 0.11 and the alternative being that the proportion is less than 0.11. They then tell us the power of the test to detect that P is 0.05 is 0.937, and we're asked to interpret the value in context. When we're asked to interpret the power, they're always going to give us like a target value, like that 0.05 down there. Notice that's not alpha, and we've seen a lot of alphas equals 0.05, but this is truly the proportion. If the proportion of subjects that develop ADHD is as low as 5% or 0.05. So in terms of interpreting the power, I want you to remember, yes, it's the probability of avoiding type 2 error. But what that would also mean, if you're avoiding a type 2 or a false negative, avoiding a false negative would be like getting a true positive. Okay, so yes, you're avoiding the false negative, but because you're avoiding the false negative, you're getting the true positive, because if the negative would be false, then the positive would have to be true. And that's going to inform how we answer this question. So to interpret, if the true proportion of all children like those in the study who would develop ADHD with the vitamin supplement is 0.05. By the way, the reason we're talking about all children is because notice that right here it said P equals 0.05, not P hat. Okay, so that's a reference to a parameter, not a statistic. Okay. So again, where are we at? If the true proportion of all children like those in the study who would develop ADHD with the vitamin supplement is 0.05, there is a power, so 0.937 probability that the company will find convincing evidence for the alternative hypothesis. Okay, that's the same thing as a 0.937 probability of rejecting the null. And that would be a truly and positively rejecting the null. Okay, now that's not exactly like a canned response. It's sort of, right? But I think the thing that makes it easier to remember what to do here is, yes, the power is the probability of avoiding, thank you for not telling me I misspelled that, of avoiding a type 2 error or of avoiding a false negative. So everything we talk about is going to be the probability of getting a true positive. Remember that positive means that we're rejecting the null. Okay, and that's a way to keep that straight. Okay, here are things that you need to know, and if you are taking the AP exam this year, and if you're actually in my class, I want you to pause the video and write these down. It is classic that you'll be asked this in the multiple choice section of the test. I'd say basically every year they do this. Okay, so things that you need to know. Ways of increasing the power, which generally as a researcher, bigger power is good as long as we don't have to get too large an alpha, because one of the ways we get more power is we increase alpha. Remember, alpha is the probability of getting a type 1 error, so we want to be really careful because you can't have it all. You can't have a really low type 1 error rate and a really low. You can't lower both the alpha and the 1 minus beta, the power at the same time. Okay, so ways we can do that. To get stronger power or to get more power, we can increase the sample size. That's the best way, that's the easiest. You could make alpha larger. Okay, if you make alpha larger and you accept more type 1 errors, then you're going to avoid type 2 more often. And if the null and the alternative parameter values are further apart. So I want to bring that into context. The one we had just a minute ago, we had p was equal to 0.11, and then we had the alternative parameter that we were talking about. They said, okay, if it's actually 0.05 in that past example. Okay, so those are ways of influencing the power. If you made this value smaller, that would increase the power. If you made it closer to 0.11, that would decrease the power. And why is that? What this is saying is, if we thought this was the proportion, but it actually for the population was this, that's pretty far away. And so since it's so far away, we're likely to find that evidence and get a true positive. Even on a small sample size, we're likely to get a true positive result, rejecting the null hypothesis. But if, for example, if p for the population was truly 0.10, that's pretty close right here. And so we're much less likely to get a true positive result that allows us to reject the null. Okay, so again, this is classic multiple choice question. Make sure you have those down. Now let's try another question that's similar to questions that we would expect to see on the AP exam. For the AP exam, it would look exactly like this. You would not see this stuff below. That's just for us today. Okay, let's go for it. The level of dissolved oxygen, which they're going to call DO apparently, dissolved oxygen, in a stream or river is an important indicator of the water's ability to support aquatic life, because fish gotta breathe. A researcher measures the DO levels at 30 randomly chosen locations along a stream. Here are the results in milligrams per liter. Mean, x bar, 4.77. Standard deviation, S sub x, 0.939. An average dissolved oxygen level below 5 puts aquatic life at risk. Do the data provide convincing evidence at the alpha equals 0.05 significance level that aquatic life in this stream is at risk? People, what I'd like you to do is pause the video. We did one of these earlier in the lesson today, and we did these in the previous videos as well. I want you to try to do this whole question on your own, and then, of course, you can hit play and see how you did, but I think you are ready to attempt this question. So if you're feeling it, please do that now. Okay, let's fill out our stuff here. We need our parameter. Our parameter is going to be mu, which is the average dissolved oxygen in convincing evidence that the aquatic life in the stream. So average dissolved oxygen in this stream. Okay, what is our statistic? Our statistic is x bar, and that equals 4.77. Notice that the parameter and the statistic are always going to be the same thing, so both means, and they're different symbols because one's a statistic, one's a parameter. They told us alpha was 0.05 in the hypotheses, so we're going to need a null and an alternative hypothesis, so that mu equals 5, and they said, is it at risk? And that happens at 5, and it would be at risk if mu was less than 5. We're dealing with a mean, so our procedure is going to be a t-test. Let's check the conditions. Do we have randomness? They said that they are going to do randomly chosen locations. So I'm going to put right here, randomly chosen. Check. Do we meet the 10% condition? So I'm going to say 30 is less than 10% of all, what did they choose? Locations along a stream. I mean, I guess there could be infinitely many locations along a stream, right? Of all locations on a stream. And then we need a normality condition. And what I'm going to say, since n equals 30, the central limit theorem applies. Check, check. Awesome. Those parts are done. Now we get to actually do the test. So let's fill in that information in the calculator. So go to your calculator, please. Menu, statistics, and we're doing a test. Hopefully you're not still clicking on confidence intervals because we're doing tests here. And we're going to do a t-test. Now this time is going to be different than the time before. Before we input a data list, but we don't have that this time. So we're going to have to go down and change this to stats. And that's going to now change our inputs. And so let's fill it in. This is asking your null value. So look back at your null hypothesis. Our null was 5. X bar comes from the sample. That was 4.77. They also gave us the standard deviation, which was 0.939. And the sample size was 30. Don't forget your alternative hypothesis. Sometimes people do that. We were concerned that we would have less than the amount of dissolved oxygen, less than 5. Now, just so you know, when we did the first example in the video and we put in that list of data, the calculator was finding all these things for us. So if these statistics are given, then you just fill them in. If they're not, but you have the data, then you fill them in, and the calculator, in fact, remember, it even told us what X bar was, and I wrote it down this time. So it'll do that behind the scenes if you have the data. Let's figure out what this is. All right, and there's my information. So I'm going to take that back over to my notebook, and I'm going to start filling it in. And so we're going to draw a picture. What was the test statistic? The test statistic is t, which is -1 point, oh cool, a -1. So negative t equals -1.34. I'll show you why that makes sense in just a minute. 342 is what I'm going to round it to. And they told us the p-value was p-value. By the way, guys, never write p for p-value because p sounds like it's a proportion, so please be careful. Okay, the p-value is 0.095. And so if 0 is in the middle and our -1.342 is right there, this right here says we're shading to the left. That's why we're getting a negative value for the standardized test statistic. And then we're going to label that that's the p-value, 0.095. Okay, this stuff is if you were going to show all the handwritten work like we had to back in the day. You don't necessarily have to do that anymore though. It's time for us to write our conclusion. We know our significance level is 0.05. We know our p-value is 0.095, and so the p-value is bigger than that. So let's write out our statement. Since our p-value, which is equal to 0.095, is greater than alpha, which equals 0.05, we fail to reject the null. And then what I'm going to say is we have weak but not convincing evidence. I'll explain why in just a second. We have weak but not convincing evidence, that what? Let's go back up and look at our parameter. That the average dissolved oxygen in this stream, I'm going to put the mean dissolved oxygen in this stream is less than 5. Now, what's up with the weak but not convincing? Okay, we don't want to say we have no evidence because we actually do have some evidence. Just think about it. If you didn't know anything about statistics and we were learning about streams and I told you, hey, anytime that the dissolved oxygen is below 5, it's a problem for the animals in there, for the life in there. And we did a whole bunch of sampling and the average we got was less than 5. That is some evidence. What this is saying is that's not enough evidence that we can be relatively sure that throughout the stream that the oxygen is too low. But we do have some evidence, and that would cause us to want to do something like, for example, maybe do more sampling with a larger sample size. If we got that same result with a larger sample size, we probably would find a statistically significant result, and we probably potentially would be able to reject the null hypothesis. This happens all the time in real research. You'll get a situation where you fail to reject the null, but it's interesting. If you have a true interest in life in this stream and you get that result, you're going, wait a minute, we need to do more research on this. We need to look into this because that is concerning. Okay, so but I have to say that that's not convincing evidence. We can't make a claim like, oh, yep, the dissolved oxygen is definitely too low. We can't say something like that. Can a 6-month exercise program increase the total body bone mineral content, TBBMC, that's an awesome acronym, of young women? So total body bone mineral content. It sounds like bone density, sort of. A team of researchers is planning to study to examine this question. The researchers would like to perform a test of null hypothesis, mu equals 0, against the alternative hypothesis that mu is greater than 0, where mu is the true mean percent change in TBBMC during the exercise program. So basically it's like a match pairs here, guys. They're going to compare a person's TBBMC before and after a 6-month exercise program. And we have 3 questions to answer here. The power of the test to detect a mean increase in TBBMC of 1% using alpha equals 0.05 and n equals 25 is 0.80. Interpret this value. So this would be a good one to try on your own. If you're doing it with me, I want to remind you that the power is, yes, it's avoiding type 2, avoiding a false negative, which is the same thing as getting a true positive. True positive. So it would be like this, a true positive and a true positive of 1%. So we could say something like this. Assuming that mu is 0.1, so or is 1%, I'll say is 1%, we'll write it the way they wrote it, is 1%. There is a p-value, or excuse me, not p-value, power, there is a 0.80 probability that we find evidence that, so that's a true positive, that the mu is greater than 0. Okay, and that's just a fancy long way in context of saying that's the probability, assuming that alternative parameter they gave us here, assuming that's true, then there is an 80% chance that we are going to find evidence that there was a positive change in TBBMC. Okay. Number 2, find the probability of a type 1 error and the probability of a type 2 error. Okay, so probability of type 1, that's just alpha. And so I'm going to write that here to remind you of that. That's alpha, which is 0.05. And remember, we said that the power of the test is 1 minus the probability of a type 2 error. So what is the probability of a type 2 error then? Well, it's the complement of the power. The probability of a type 2 error then is going to be 0.2. Number 3, determine whether each of the following changes would increase or decrease the power of your test and explain your answers. All right, A, we're going to use alpha of 0.01 instead of an alpha of 0.05. I want to remind you that one of the ways of increasing the power is to also increase alpha. And so if we decrease alpha, that is going to decrease the power. Okay, they kind of move in the same direction. Okay, higher alpha means higher power, lower alpha means lower power. What about part B? Using a sample size of 100 instead of a sample size of 25. That's going to increase the power. One of the things that increases the power is an increased sample size. So that is going to generate an increase in the power. So that's going to be all for today. Enjoy practicing, and I'll see you next time.